So today we're going to talk about, well, I've called it chiral liquid crystals or chirality in liquid crystals. But I will try and mention things like, just in the mission of the workshop, in solid state materials, I would like to mention a bit of biology and so on as well. But it's mainly about liquid crystals, this talk, and I will start with a short overview. This is only going to be short about chirality. We'll then give you a bit of an indication what liquid crystals are, only the simplest bits. And then we go into chiral liquid crystals. And I've picked three topics there. One of them is the cholesteric phase or chiral nematic phase, then frustrated phases, and ferroelectric liquid crystals. And what we observe for chiral liquid crystals is basically novel structures, novel phases, and novel effects, sometimes in combination of all three of them. You might wonder about the beetles down here. That's the biology part. I will come back to those later on. So, chirality. We are actually living in a chiral world. There is plants that grow in a chiral fashion with a helical structure. There's the right-hand beans growing, whereas the pop grows in the other direction, left-handed. There are chiral animals like flunders or this guy. By the way, I did nick a number of pictures from the internet without reference. So students don't do that. But that was the only way I could actually find them. If you remember the old days at school, maybe, there were actually chairs like this for left-handers and right-handers. So you have your little table fixed there for left and right-handers. Does any one of you play golf? No. Well, neither do I, but apparently there are golf clubs that are for left-handed people and for right-handed people. Scissors, you might appreciate that these are available in left and right versions, especially the left-handed people usually appreciate that because there's less of them for some reason. I don't know why, but it happens to be that way. Well, since the whole thing is about knots, knots can of course be chiral as well. And another example would be Möbius bands. And in line with a definition of chirality, our old friend W.H. Thomson, the later Lord Kelvin, he said that he would define chirality, or he calls any geometrical figure, our groups of points, chiral, and say it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincidence with itself. So basically, chirality defines itself through the absence of mirror symmetry. And we know that this is often the case in chemistry, where we have left and right-handed molecules. And interestingly enough, if you look at the amino acids, all of the amino acids, all of these guys here, except the very first one, The very first one is A chiral, the smallest one. But all other ones are all left-handed. And sugars, similarly, are all right-handed. You can have glucose, fructose, and so on. You can polymerize them so that they become cellulose or starch. You can combine them into sucralose. All of these are right-handed. So there must be some kind of idea behind this that nature has. And we might come back to this in a bit. Because the important part of it is that all of the biologically active molecules are actually chiral, right? And these are molecules like DNA, proteins, but also medically active drugs and so on. They, for example, painkillers, they are in nearly all of the cases chiral. And one of the nice examples is not fully shown on the screen, but if you take the molecule limonene, that in one configuration, the S configuration, smells of lemon, whereas if you look at the molecule that is mirror image, this one here, so that's in our configuration, smells of orange. There are more examples like that. DNA as a helical molecule is of course chiral, and that's of course important from when in the replication of genes and so on, where the DNA is transcribed into RNA, which then translates into a sequence of amino acids. And remember, these are all chiral, they're all left-handed. And these amino acids then make up the proteins. So there is a biological aspect of this as well. And right, so why do I mention all this? Well, first of all, because chirality is essential to biological functionality. And secondly, many of these biological molecules are in fact liquid crystals. And these are special types of liquid crystals. There are two sorts of liquid crystals, thermotropic ones that are made up when you change the temperature, and lyotropic ones when you change concentration in an isotropic solvent. Right? So, a bit about liquid crystals. They were first discovered in 1888 by an Austrian botanist called Friedrich Reinitzer. This is a picture, looks very much like an academic at its time. And he was looking for this kind of molecule here, which he isolated by chopping up carrots. And this is polystyryl benzoate. And he isolated that from the carrots, looked at them and said, well, there are two melting points. And that, of course, can't be. So two melting points were out of the question at that time. I mean, at that time, people didn't even know about atoms, right? So that just couldn't be. There was gases, liquids, and solids, and that was it. And nobody really believed him. He sent the samples to Otto Lehmann, who was a German physicist at the University of Karlsruhe, who was actually the successor of Heinrich Hertz, the one with the frequency, Hertz. And already 1 year later, in 1889, he coined the term liquid crystal and actually realized that this must be the fourth state of matter. And as a fourth state of matter, what he said was, okay, things go from a crystalline state into a liquid crystal state, from a liquid crystal state into an isotropic liquid, and then into a gas. Not all materials do that, but some of them. And by now we have about 150,000 chemical compounds that actually are liquid crystallized. Okay, so but nowadays we basically know that well, they're very useful as optical elements, especially in displays. I mean, your little TVs and the large TVs and screens on your laptops and so on. These are all liquid crystals. This picture down here is the 1972 prototype of Chirality Helfrich, who discovered the twisted pneumatic on which all of these liquid crystal displays are actually based. And I believe there are two of these still around. One of them is at a museum in Karlsruhe, and I think the other one, Martin Schardt has at home, I think. So, well, 50 years later, we have huge TV sets built mainly in Japan, the big ones at least. And so that's what liquid crystals are being used for. Now, I said there's two different types, thermotropic and lyotropic liquid crystals. The thermotropic ones are the ones that come by changing the temperature. So we start out with a crystal, we increase the temperature, and we can then go into things that are soft crystal phases. Sometimes there are hexatic phases, and then there are fluid smectic phases like smectic C, which is tilted phase, smectic A, which is an orthogonal phase, still with one-dimensional positional order. That order is lost in the pneumatic phase, which only has orientational order. And later on, once we heat this still further, we get to the isotropic phase. And we can tell these apart, not all of them, but a lot of them, with a lot of practice in sterilizing microscopy, for example, because they all show quite characteristic textures with topological defects and things like that. And the isotropic phase then appears black, because there's no birefringence anymore. Okay, so basically we go from a crystalline state to a liquid crystal state into an isotropic liquid. The liquid crystal state will be strongly light scattering. That's how you can, it's really fluid, but strongly light scattering. So it's sort of like a milky liquid. Okay, so these can be distinguished by polarizing microscopy, and this has been done ever since liquid crystals were discovered. So we distinguish these phases also by their molecular shapes. They can be sort of rod-like, which are then called palamitic. They can be disc-like, discotic, bent core. Liquid crystals have been around for about 30 years now, and bowling liquid crystals as well. And here are just some examples of these sort of structures. Okay, so physicists and chemists usually have a very different view on liquid crystals. Physicists usually see them as something like this, a rod-shaped something without any structure, but much longer than light. Right? So the length is about 30 angstroms, roughly, of a liquid crystal molecule, and the width is about 4 to 5 angstroms. The chemists, of course, say, oh, no, these are much more complicated. these look like this. There are benzene rings and all sorts of groups and so on. I usually prefer the viewpoint in the middle. There's a polarizable central core and there's floppy chains on the ends. Okay, so but we have elongated systems that are partially ordered, and this leads to anisotropic properties like birefringence or dielectric anisotropy, or viscosity and elasticity and all sorts of things. So here is shown the refractive index as a function of temperature. In the crystalline state, you have an extraordinary refractive index and you have an ordinary refractive index. And these become equivalent when you come to the isotropic liquid, which then just has a refractive index. Okay, but you can see this transition very easily in a polarizing microscope, and you start out with the black texture of an isotropic liquid, and you cool it down. When you cool it down, there will be the liquid crystal forming, which will be bright because there's birefringence. So this is basically the transition to a liquid crystal phase from the isotropic. So the black part is the isotropic. This is not quite finished yet, but the black part is the isotropic, and the colorful bits are the liquid crystal. Okay, so there are some other liquid crystals that are called lyotropic ones, and they are actually much lesser known, but they are probably closer to you than you might think. They're used a lot in detergents. These are made from amphiphilic molecules. And amphiphilic molecules in the presence of water at the right concentration makes a liquid crystal. So in detergents, soaps, you find liquid crystalline structures. The cell membrane is pretty much a bilayer, which is of a liquid crystalline structure, and in there we also have our proteins again, which are also of course related to chirality. So you start out by taking your free amphiphilic molecules, adding them to water, and at very low concentrations, you have free amphipols floating around in water. They then, at the critical micelle concentration, form or agglomerate into micelles like this. It can be disc-shaped, or they can be rod-shaped or spherical. And if you increase the concentration further, you eventually get to a liquid crystal phase. And oftentimes this is a hexagonal phase, and there can be some cubic phases in between as well. And this is the lamella phase, and you can already see these lamella, they look very similar to the cell membranes. Right, and here's an example, the hexagonal phase here. This black part is actually the cubic phase, because that will not have birefringence either, so it appears black in microscopy. And then you have a thin bit of a lamella phase out here. And you can study this by X-ray diffraction, for example, and you can come up with quite complicated structures besides the hexagonal and the lamella phase. Especially the cubic phases are relatively complicated. Okay, so, and now we introduce chirality. So we take our isotropic liquid, We have an achiral liquid. We do the same thing, make this out of the chiral molecules. So we get a chiral isotropic liquid. What's the difference between a chiral isotropic liquid and an achiral one? You're sitting at the front. You know.
I guess it's structure.
The structure will be different, yeah, but in properties.
Oh, mirror, if we
No, you just use one structure. Optical activity. Right? All the chiral ones would be optically active, whereas an achiral liquid like water is not optically active. If you put sugar into water, it turns the polarization plane off of polarized light. Okay, but the more equivalent of a liquid crystal system would probably be what is called the blue phases. These still appear that they're still isotropic because they're cubic, but they are actually liquid crystalline and have some very different effects as well. Then you can do the same thing with a pneumatic phase. So this has only orientational order. You make this chiral, either by making the molecules chiral or by adding little chiral molecules, that works as well. And you get the helical structure. This is called the chiral pneumatic phase or the polysteric phase. Same thing. Polysteric because all the way back to chopping up the carrots, this was cholesterol benzoate, right? That's why they were called polysteric phase. So the first phase that Friedrich Leibniz looked at was actually a chiral liquid crystal. And it did actually have a blue phase as well. If you can read German, then you find out that he actually writes about this in his old paper. But he didn't realize that there were two liquid crystal phases. And so it was only rediscovered in the about 100 years later, actually. Okay, smectic A. If we make that chiral, what happens? Well, again, you can do the optical activity thing, but you can also have structural chirality by the formation of twist grain boundary phases. Now the twist is actually not allowed in smectic A, so it has to break up into a little smectic A, mediated by grain boundaries, which are made up of screw dislocation. Now this is complicated, right? But there is an analogy to solid state physics. And we can have smectic C, we make that chiral, we get to the chirosmectic C phase, and that forms a helical superstructure as well, and a ferroelectric. And we get to that in later. Okay, so let's start with the polysteric phase, the easiest one. If we make our pneumatic chiral, we get a chiropneumatic or polysteric phase, and that can be left-handed or right-handed. And that depends on the molecular configuration of the molecules you use. Right? The scale-up properties like the phase transitions, the viscosity, elasticity, and so on, will all be equal. Only the chiral properties like the pitch of these helices, they will be equivalent, but change the sign. So that's the only difference between the left-handed and the right-handed one. You can also see this in optical rotation dispersion. One of them will turn in one way and the other one will turn in the other way. And we can't really tell even now, we cannot tell which configuration actually makes a left-handed and which makes a right-handed helix. You just simply cannot tell. But what you can tell is that there are optical phenomena related to this, and this is called selective reflection. So if you apply Maxwell's equations to a helical medium, then you will, after a lengthy calculation, find out that there is light being reflected from that helix. And that light is dependent, or the wavelength of the light that is reflected depends on the pitch, which is a function of temperature, and it depends on the average refractive index. And that means we basically have a photonic band gap. And the width of this photonic band gap is proportional again to the pitch and the birefringence. Now, this is all for normal incidents. It becomes a bit more complicated if it's not normal incidents. So, but if we put linear polarized light onto a helical structure, linear polarized light is the superposition of left and right-handed light. One of the handednesses of the light will be reflected, the other one will go through. So we can have a maximum of 50% of the light being reflected. And this is actually shown here. This is reflection as a function of wavelength. And there is a photonic band gap here at around 550 nanometers. Right? Depends on the pitch where this thing is. You can make it in the microwave, in the micrometer region, also on the depends just on the pitch here in that formula. And that pitch is temperature dependent, as you can see here. So by lowering the temperature, we shift to the longer wavelength band, which is not the typical way, but you can construct it that way if you want to. Normally, the pitch becomes shorter as you increase the temperature. But you can make mixtures that do the opposite. Okay, and this is being used in many different areas, actually. It's used in medical thermography, basically relating to the difference in heat. Right, so what you see is inflammation, for example, are hotter than the rest of the body temperature. So that would be blue, and then the rest would be, well, going to green, red, and so on. Same thing for inflamed teeth. You can also use it as circuit board testing. Many decades ago, we used it for the detections of shunts in thin film solar cells, for example. It's used in cosmetics, fashion, these mood rings that change color depending on your mood. Those are how have pulsarity. I don't know if this is popular here, these car paints that change color when they pass by. I would think that is very popular in Japan. But that you can do with polysteric helical structures rather than polymerized as a paint. Or you can make just other cool stuff. So this is applications of selective reflection. Now, if we go back 150, 170 years to our friend Louis Pasteur, he said that, well, you can have left-handed molecules, you can have right-handed molecules, but you can't interchange them. And the left-handed ones will always be left-handed, the right-handed ones will always be right-handed. This is not true. At least not in liquid crystals. And if you take this molecule, for example, which was actually developed in Boulder. I think the first one was, what's their chemistry colleague? Dave Wolver. Well, Dave Wolver, he synthesized that, but he didn't realize that. He would have also found a TGB phase in there. But it's a very, very nice molecule. So that actually shows an inversion of structural chirality if you change the temperature. So you start out with a right-handed pitch, which then diverges at a certain temperature. And if you lower the temperature further, you come down again with a left-handed pitch. So that clearly inverts chirality. But up to now, all the molecules that I've seen that have this kind of effect, they all have two different chiral centers or more. Anyway, you can use this by making, for example, polymer networks in a polysteric liquid crystal, which you can actually see by what is called polygon cuts. These are these sort of arced structures here, which you get when you take a helical structure and cut it at an oblique angle. Then you end up with structures that make these arcs. And you find that exactly in these polymers as well. And if you fill this with a liquid crystal of the opposite handedness, or if you use a twist inversion compound where you form your polymer network when it's right-handed and you go to temperatures where it's left-handed, then you can actually get to reflections, or in this case, this is the transmitted light. So you can go beyond these 50% that are usually seen as the theoretical limit. Okay, so what can we do with laser? With these band gaps. So one thing that we can do is we can make tunable lasers from that. So you pump your laser at the lower end of the band gap, and you will observe an emission at the higher end of the band gap. And you're going to have a fluorescence first, and then once you get over the pump threshold of your lasing system, then you have lasing lines, and these can vary by all sorts of different methods. You can vary them by changing the temperature, which changes the pitch, which changes the position of the band gap, or you can have a pitch gradient, which you can actually even get for a glassy system. So you can cool that into a glass and it will stay like this. And depending on position what you take, where you have your lasing, you can tune your wavelength, and that works pretty well. Or you can even do this by applying electric fields. And so this is one way of making tunable lasers, for example, by using polysteric crystals. Okay, there are other things. This is not a chirality related effect. This is but it's only observed for cholesterics, really, and it can only be used in cholesterics to a certain extent. So that's the flexoelectro-optic effect. So flexoelectricity is basically you apply a deformation and you get a polarization, or the other way around, you orient your polarization, which causes a deformation of your sample. And if you take a cholesteric structure and you have your helix like this, and you turn your helix by 90 degrees so that it's like this, and you make the pitch short enough so that you cannot see it anymore optically. So, for example, in the visible, right? That's below the resolution limit of any microscope, optical microscope, I should say. Then, so if these lines here, which are corresponding to the helical structure, if they become so close together that you can't revolve them, and you have them all pointing in one direction, then that thing will look like a birefringent plate. But it's a birefringent plate of a liquid crystal, and you can apply an electric field, and you can turn your optic axis either the positive way or the negative way, depending on the polarity of the field. And the angle is proportional to E, the electric field that you apply. And so you have a linear effect, at least to some degrees. When you get close to phase transitions, then that doesn't hold anymore. But you have a linear effect, and it's proportional to the pitch, which you can see here. This is the pitch, the open symbols, and the closed symbols is the response that you get as in angle. So that is pretty equivalent. So that is one of the effects that you can make, which is well suitable for grayscale generation. It is fast in the order of microseconds, and the problem with it is that the light modulation is actually not that large. You would want a bit more than these 4 or 5 degrees of switching of your optic axis. Okay, so other optical thin films. From that's getting us back a bit again to biology. So trees. We're starting out with a tree, and we're chopping this down all the way to cellulose nanocrystals. Right? And cellulose nanocrystals, if you disperse them in water, they will actually make a liquid crystal phase. So at least at a certain concentration or a concentration range. So at 3% of nanocrystals in water, nothing much is happening. That's still water, but so it's molecularly dispersed, really. But then you see that you're going through a biphasic region, and your liquid crystal becomes more and more. And by around 10–12%, all of your solution will be liquid crystalline, which you can see here as a texture in polarizing microscopy. The pitch of this will make a cholesteric structure because, as we said, cellulose is polymerized sugar. All the sugars are chiral; they're right-handed. the helix is left-handed that they make. But that's why I'm saying from the configuration of the molecule, you could not say what kind of helix they make. But all the sugars make left-handed helixes. And the pitch is about 8 microns, and it's pretty much temperature independent, but it depends on the volume fraction of your cellulose nanocrystals. And the more cellulose you put in, the smaller the pitch becomes, which does make sense because they're chiral. The more chiral you make your system, the smaller the pitch of your helical structure becomes. And if you then dry off your water, then you end up with optical films that show selective reflection in the optical regime. So around 700 nanometers all the way down to 400 nanometers. And you can make these films relatively big. This is 5 centimeters here. And so you can make optical solid films on glass plates or whatever, with lyotropic liquid crystals or lyotropic cholesteric crystals. A bit more here on biology. We've talked about DNA before. If you put DNA in water, it makes a cholesteric phase. I don't know if you can see that from the front you might. From the back I'm not sure, that there are lines across here. Do you see dark lines? They're not artifacts, they're actually there. And these lines are due to the cholesteric helix. Because whenever your optic axis, whenever your molecules point along the direction of light propagation, there's no birefringence, it will be dark. And it's doing this, it will be dark, and doing that, and so on. So the distance between two of these lines will actually give you the pitch of your helix. And you can do this with shorter DNA bits as well. This is actually a study from, I think it came out of Noel Clark's group in Boulder, who made short controlled bit of DNA, and then have different liquid crystal phases here that are related to the length of the structure. And you can make it shorter, and you can make it even very short, and then you can actually add these up and stack them end to end, and do this in a controlled way, and generate liquid crystalline phases of DNA. Right, so the short DNA segments, the really short ones, at certain concentrations at least, do not show liquid crystal phases, but when combined, they become longer, and then they stack up and form liquid crystal phases. Okay, so frustrated liquid crystals. Well, first of all, frustrated liquid crystals only show up in small temperature regimes. That's why they're frustrated. And one of these is, I mean, when I say small temperature regimes, I mean about 1 degree or less, usually. There are always exceptions to any of these rules. Whenever I say something as a rule of thumb, there's always an exception, right? So these blue phases, they come between the isotropic and the cholesteric phase. And they are built up of double twist cylinders. So you have a twist in one direction and a twist in the other. So double twisted cylinders like this. And if you come from, let's say, the high end of your temperatures, there is an amorphous blue phase 3, which is also called the blue fall, and so on, which is a cubic phase, but only local. Right, so it's locally cubic, but the cubes don't really know what the other cubes are doing. Further down, you get to a simple cubic phase of these double twisted cylinders and the bicenter cubic phase. So the dependence here is you change the temperature. This is your chirality. This is all strongly dependent on chirality. So if you only have a medium chiral system, it will only show the cholesteric phase. If you make your system highly chiral, then you can observe blue phase 3, and you make it less chiral, you come to blue phase 2, less chiral, you come to blue phase 1. Or you can do the same thing by changing temperature. You can also get different blue phases by changing the temperature. Which one of the cubic phases you have, you can do by what is called the bicosal lines. That's basically microscopy in convergent light. So not everything is in focus, your focal plane will be out there, and you get different figures depending on your blue phases and the different Miller indices and so on of your structure. So you can check this, what kind of blue phases you have. And again, this blue phase, because you have chirality and a helical superstructure in these double twist cylinders, there is selective reflection again, which is related to the average refractive index, the lattice constant, and the Miller index. And again, you can also use this for lasing. You have your fluorescent background here, and that's what happens up here. This is the pump intensity or the pump energy here, and this is the laser intensity as a function of pump energy. And as you reach the threshold for the pump energy, you have lasing starting, and you have your laser line. So blue phases can be used as lasers as well. You can polymer stabilize them, and you can show that there really are cubic structures. And these polymer stabilized phases, they actually show a rather large Kerr effect. So the Kerr effect is an induced polarization, which is proportional to the square of the electric field. And that, you can see here, works pretty well. And it has a few advantages. One of them is that it's fast. It is quite obviously linear as a function of E squared. And you don't need alignment layers, which is, when you build displays, really good. Because that's the only place where you bring in dust, is when you rub your glass plates to get alignment. Now you spin coat your polymers, you rub them, and then you align your molecules with that, and that's what creates dust. And displays are about 5 microns thick, and dust is usually bigger. And that's a problem, because all of these displays you can't sell. Right, so that is why everything is very, very clean in the display production facilities. Right, so and they did show well, that was still 15-inch or so, but a blue phase liquid crystal display the world's first, and I should say the only. This is a picture taken back in '97 at a display conference. And we still don't have blue face displays. The reason being, it doesn't seem to be reproducible. You can only reproduce it by following the absolutely same procedure as the original authors did. But as soon as you use other mixtures of polymers, it doesn't work anymore, which is a bit of a problem, because then you don't really have much to optimize. But it was a very nice display. Okay, so the other, yes.
Are there stable across the large range of temperature?
Well, that was the idea, yes.
That's the point of using a polymer.
That's the point of using polymer stabilization, yes, is to widen the phase existence range. Because otherwise you would have to heat your display and keep the temperature constant at exactly 48.7 degrees. And that's not feasible. And yeah, yeah, it was originally claimed that they had like 50 degrees of blue phase range. And if you do it with other polymers or something, there is an effect, no doubt. But you know, you change from 1 degree to 7 degrees maybe, or to 5, but never to the 50 degree. At least I never succeeded in doing that. Okay, so another frustrated phase, or actually it's a set of phases, the twist grain boundary phases, and they occur between the cholesteric and the phlegmatic phases. And this is where you have the relations to solid state physics. Because the twist grain boundary phase is the equivalent, or the liquid crystal equivalent, to the abricosal phase of a superconductor, right? Where you have the magnetic field here, and that is exchanged for the chirality here, right? And you increase chirality, you make your TGV phase larger. If you change the temperature, the same thing happens. So there's a whole list of liquid crystal properties that can be directly translated into superconducting properties. And this was first sort of realized in the end of the 1980s by Wren and Tom Lubensky. And then it was realized that from a synthetic point of view, already 1 year later by John Goodby. And that's why I'm saying Dave Walbach could have done this 5 years earlier if he would have known that there was a TGV phase, that it actually existed. Okay, so this is basically what's happening is that the twist of the cholesteric phase is not allowed in the smectic A phase. So there's a competition between twisting and layering, and that is being resolved by introducing screw dislocations, which form an array, and this array of screw dislocations acts as a grain boundary between smectic A blocks of different twists. And that's how the structure supposedly looks. And the transition enthalpies that you have are actually very small, well, quite hard to see. It depends very much on chirality. So if you decrease the chirality of your system, the TGB phases will vanish, but they can be commensurate or they can be incommensurate. Both of these cases have been seen. And this is an example here from an X-ray study by Laurence Navai, who looked at a commensurate TGB phase. And you see all these little dots here that you would expect. I think it's about 18 or so on this spot, which gives you the dimensions of the blocks and things like that you can calculate from that. If you look at this in the microscope under conditions where the SMECTI A phase is oriented such that the optic axis points along the direction of light propagation, everything is flat, and the twist gain grain boundary phase you can see here. If you actually zoom into this, you will see that there are equidistant patterns of lines as well. So there is actually a helical structure. And then you have the cholesteric phase up here. There's a clear difference in birefringence. So they really do exist, but over very small temperature ranges again. And they exist in a TGB-A form, where the blocks will have a symmetric A structure, but they can also have a symmetric C structure. And there's, I think, 3 different variants of that. But the TGB-C phase, you can often see as a sort of square grid pattern in microscopy. Right, ferroelectric liquid crystals. Now, it was Bob Meyer, who sadly left us not very long ago, who realized that all tilted chiral symmetric phases possess spontaneous polarization. And that means they are pyroelectric. And if you can switch this polarization between 2 stable states, then you have a ferroelectric. So ferroelectricity is a subgroup of pyroelectricity. And this does happen in tilted pyrosymmetric phases. Not all of them you can switch, especially the soft crystal phases you cannot, but you can switch symmetric C, for example, or the hexatic phases, symmetric I and symmetric F. You can switch those as well. But in symmetric C, you have, again, not only ferroelectricity, the formation of polarization, but you also have the formation of a helical superstructure. And that forms to compensate the polarization at a short scale. So basically, what you have is you have your molecule, it tilts within your layer, and then it progresses like this. Or it's easier to show it this way. So you have your symmetric layers like this, and your helix goes this way. The polarization that goes with it is related to these 2 theta, this opening angle, and that goes like this. So it compensates over 1 pitch. And you can see the line pattern here. That's a bit more obvious to see in this one. So the distance between 2 of these lines is equal to the helical pitch that is being observed.
Just a question regarding this. Does this mean that there is a net polarization of the molecule? Besides being chiral, each molecule has a net polarization that is non-zero.
Yeah. but usually that would disappear. It's like that. I'm going to show you the symmetry argument in just a bit. Is there any solid state physicists in here? You are. Then you might know that it is pretty hard to show ferroelectric domains, right?
Yes. For sure.
It's not easy. Very easy. You just use liquid crystals. You put them in thin cells, that's it. And this idea actually came by Noel Clark and Sven Lagerwald. And they said, okay, if we put our helical symmetric C phase into a gap that is smaller than the pitch of the helix, then the helix will basically be unwound, and we are left with the two domains. So you have this sort of structure, and you put that in a cell, and you're left with either that or that direction, right? So plus theta and minus theta. And that's it. And those are your two domains. And between those two domains, you can switch back and forth by changing the polarity of your. Okay, this is where your question comes in. Right, so if you have an achiral symmetric C phase and an arbitrary dipole moment, then you have a inversion center here. You have a mirror plane in the X, that plane, and you have a twofold rotation axis in the Y direction. And so if you apply these symmetry elements to your arbitrary dipole moment, you end up with 0. Right? Because your arbitrary dipole moment, applying inversion symmetry gives you a negative of that, so the total is 0. If you do the same thing for chiral symmetric C, then your inversion center and the mirror plane vanish. And you're only left with your twofold rotation axis. And that means your arbitrary dipole moment, if you apply the rotation, ends up like this. The two terms in X and Z are 0, and the one in Y remains. So that basically means that your polarization will always be in the plane of the symmetric layer. So this is basically the symmetry argument of Bob Meyer. And then they made the molecules, and hooray, they have ferroelectric liquid crystals. Since then, there was a bit of development. You do not only have ferroelectric states, you can also have ferrielectric states and antiferroelectric states. So all of these that you know from solid state physics do occur as well. And I presume that you're familiar with the Landau theory for, okay. So Landau expansion for the ferroelectric liquid crystals. You have all the Landau terms here. And you have a dipolar ordering term. And you have a bilinear coupling term. This is the coupling between polarization and tilt. And you have a biquadratic coupling term. All of these are non-chiral, except this one. That's the only chiral term in there. Right? Okay, so you can measure your tilt angle, you can measure your polarization, You plot polarization as a function of tilt angle. The linear line here for small angles gives you the bilinear coupling. The deviations here, that's your biquadratic coupling. And if you apply an electric field, well, then you have an electric field term as well, where the polarization couples to your electric field. And if you take this whole Landau expansion and minimize that with respect to the polarization and with respect to the tilt angle, you end up with these two equations. This is a bit different here. Normally you would write theta is equal to something of temperature. It's much easier when you write temperature is equal to something of theta in this case. But it's the same thing. And that basically gives you your potential of your ladder potential in the parallel phase. This is your minus theta direction. This is your plus theta direction. So your two domains. And you have to go, you have to go across this heap to get from one to the other. And that's what you do by applying the electric field. Right? Because that also changes the height of the minima and so on. So what you can do by using both of these equations, you can measure the polarization as a function of temperature and electric field. And you can measure the tilt angle as a function of temperature and electric field. And you can fit both of these simultaneously to both of these equations. And you can actually experimentally determine the complete Landau potential. So for any solid state physicist who's ever wondered how big these numbers are, that's the order of magnitude here. And then you can, of course, calculate whatever happens with your potential, and from the potential, you know, you can get basically the whole electro-optics, really. Okay, so, and the electro-optics are, of course, quite interesting for these ferroelectrics, because we said you're switching from one state to the other, right? So that means you have either transmission on or transmission off. So it is actually a sort of digital switching. But if you look at the scale here, it's much, much faster than anything else that you see with liquid crystals. It's actually in the microsecond range, the switching process. And that is the basis of the ferroelectric displays. And so the idea is basically this one. You come in with light, you polarize your light, you orient one of your states parallel to this incoming light, which is, let's say, polarization down. There will be no birefringence, and everything will be absorbed by the cross polarizer. If you then reverse your electric field, you switch to the second position, you have your polarization up, light can be transmitted. So you're switching between dark and bright. That's basically the whole idea of it. But it does have extremely low power consumption, because you only need to address that pixel that you're actually switching. And again, a bit of history, 25 years ago. Canon invested an awful lot of money into the development of ferroelectric or surface stabilized ferroelectric liquid crystal displays. These are based on the the idea of Noel Clark and Sven Lagerwald. And they patented it, and Canon bought into this patent. And this is the screen that they came up with. This is about 25 years ago, a bit longer maybe. This is Sven Lagerwald's office, by the way. I was a postdoc in his group. And this is my laptop. Bought in '97. That's how they were at the time. Absolutely awful. If you look from the side, my laptop, this is not a screensaver. All right, my laptop is not turned off. That's how bad the viewing angles actually were. But you can still see the ferroelectric one because that's switching more or less in the plane of your screen. Whereas the other one is switching out of the plane of your screen. And so the viewing characteristics were excellent. All of this was pretty excellent. Beautiful screen. A bit heavy maybe because they made a big glass plate in front of it. Because if you press at your pneumatic display, you see that it comes back after a second or two, right? That doesn't happen with ferroelectrics. You press on them and that's it. Yeah, they never came into production. And I think Canon lost an awful lot of money there. But where they are in production is again in Boulder with micro displays. This must be very old by now, but I'm still showing this in lack of better pictures. This is I think super VGA resolution on the display. Well, this is a pen, right? So they're now used in virtual reality systems and miniature projectors, in light modulators based on ferroelectrics on silicon. Camera cameras often have, especially the good ones, have ferroelectric displays in them. But you can use it in switchable holography and so on. So there is a market for them, and I think DisplayTech is selling quite a lot of them by now. You can probably confirm.
Well, it was purchased by Micron. The DisplayTech is now part of Micron. But you know, the displays are there.
Yeah, but they are. I mean, I remember that I met one person from DisplayTech way back in nearly 20 years ago, and they said they sell about 600,000 of them. So I presume it's a lot more now. Right, so why don't we have all these brilliant displays? Well, one of the reasons is they make defects. And that is something that is really, really hard to avoid. And that's a problem. You get these sort of zigzag defects because when you cool from the smectic A to the smectic C phase, you're changing your anchoring period of the smectic layer by cosine theta. And that gives rise to these zigzag defects. There are ways around this. The so-called defreeze ferroelectrics have been developed that show no layer shrinkage when you go through the transition. In a sense that they are already tilted, but in all directions, and then they only tilt in one direction when they go from smectic A to smectic C. But and your layers are basically constant. But I presume that these are very expensive to design and to make. The other thing is that there has been a development in thin film transistors. So TFTs have been built, have been invented in the meantime. And that technology basically was applied very quickly to your pneumatic displays, and you're not addressing them line by line and column by column now, but you have a load capacitor and transistor at the back of each phaser. And so you can address them much easier, quicker, and so on. The response times have gone up, have gone down, I should say, dramatically. And yeah, and basically there was no need for ferroelectrics anymore. And why use the more expensive ferroelectrics when you get the same thing with a technology that's already there? But they're still, to this day, I think the only fluid ferroelectric materials that are known to man. So there are other trends, ferroelectricity without chirality. So these are the bent core materials. You know, these banana-shaped molecules that I showed at the very, very beginning. They sort of, for steric reasons, stack up like this, and then they have in their layer, they can have a polarization which goes this way, the next layer in the other direction. So that would be anti-ferroelectric behavior, which you can see with the double current peaks here. Or you can see it also here where you switch the Maltese cross from one position to the other. Whereas when you turn the field off, that's your only stable state actually. I mean, it was called tri-stable switching at the very beginning, but of course it's not tri-stable, it's monostable with 3 different switching states. But a few years ago now, I don't know, maybe five years ago, the pneumatics came, ferroelectric pneumatics, which people were looking for probably for for centuries, for decades, let's say. Because they are considered to be the holy grail. Take a pneumatic material, we have all the production facilities and everything, and make those ferroelectric so that they can switch really, really quick. That 1,000 times quicker than the normal pneumatic. That would be the idea. The order comes through strong polar coupling, which you don't have in the normal pneumatic phase, but in the ferroelectric phase you do, and you have a polarization, which is actually really large, if this is true. Normally you have nanocoulombs per square centimeter, they have microcoulombs per square centimeter, so that's really large. And we'll see if they make it to any applications in the future. Right, coming to a conclusion. Well, as I said in the very beginning, the introduction of chirality to liquid crystal leads to a wealth of new phenomena. We have new structures, new phases that only exist in chiral materials. We have new optical phenomena, electrical phenomena. We have selective reflection, piezoelectricity, and so on. We can do second harmonic generation. We can do ferroelectricity and these kinds of things, just simply because of chirality. Well, all of these things lead, of course, to novel applications as well: electro-optic, mechano-optic, magneto-optic, in not only displays but also spatial light modulators, thermography, lasers, sensors, telecommunications, waveguides, you name it. You can do it with liquid crystals. And this is a bit of an outlook into the future now. For when I'm retired. What I think will happen in the field of pyrolytic crystals, I think it will strive in the future by employing this relationship between chirality and biology through macromolecules like DNA, RNA, but also actin, viruses, cellulose, and so on, bacteria, and so on. And I think that this will greatly enhance upcoming fields or in their development, like living liquid crystals, and yeah, something that Ivan is working on quite a lot and is solitons in liquid crystals. But also things like pattern formation, self-propulsion, biological functionality, drug release, moving drugs from here to there, things like that. I think this is where liquid crystals and chirality will have a bright future. Okay, so I hope that you have enjoyed your, I don't know how short it was actually, let's call it excursion into the field of pyrolytic crystals. And if you have any questions